A 7-ton rock exploded over Ohio on March 17th with the force of 250 tons of TNT. Nobody warned you. 4 days later, another one shook Houston. Still no warning. That is 2 atmospheric explosions over the same country in 96 hours, both invisible to every detection system we have. And here's the part nobody is saying out loud. Those were not the only 2. 6 major fireballs in 20 days. No meteor shower. No explanation. No pattern that fits anything in the official playbook. So what exactly is happening to our sky right now? And why does the answer might involve an object that arrived from outside our solar system entirely? Stay with me, because what comes next rewrites everything you thought you knew about how safe our skies actually are. Subscribe and follow along, because this story is not over. The detection gap is still open. The lab results are pending. The Texas rock is unconfirmed. And the interstellar hypothesis is still waiting for the evidence that settles it. When that evidence arrives, this channel is where you hear it first. The next event will not announce itself. You are going to want to be here when it does. Something hit us. Twice. In 4 days. And nobody knew it was coming either time. Let's start with the first one. On March 17th at 8:57 in the morning, a 7-ton rock traveling at 45,000 miles per hour entered Earth's atmosphere over Lake Erie and exploded above the farmland of Valley City, Ohio, with the force of 250 to 370 tons of TNT. To put that in perspective, the bomb dropped on Hiroshima released the equivalent of about 15,000 tons. This was smaller, yes, but it was also completely unannounced, completely undetected, and it happened 11 miles above people who were eating breakfast, driving to work, and sending their kids to school. Car alarms went off. Buildings shook. 911 switchboards lit up across multiple states. People thought something had exploded nearby. And in a way, something had. It just came from space. No asteroid warning system flagged it. No observatory issued an alert the night before. Nothing on any tracking database showed an inbound object at that location at that time. The rock simply appeared, the way only things coming from the direction of the sun can appear, and then it was gone, leaving behind a shockwave and a confirmation that our sky is less monitored than most people believe. Then, 4 days later, it happened again. On March 21st, at approximately 4:39 in the afternoon, a different object, this one estimated at around 1 ton, roughly the size of a washing machine, entered the atmosphere over the Gulf Coast and broke apart above Houston, Texas, traveling at approximately 35,000 miles per hour. That is Mach 45, 45 times the speed of sound. People across a 150-mile radius heard the sonic boom. Homes shook in one of the most densely populated metropolitan areas in the United States, a city of 7 million people, going about a regular Thursday afternoon. And once again, not a single early warning system had fired. Not one alert. Not one email from a planetary defense office. Nothing. 2 major atmospheric explosions. Same country. 96 hours apart. Both completely invisible to our detection networks until they were already burning through the sky above millions of people. Now here is the part that should make you sit up a little straighter. These 2 events did not happen in isolation. When you pull back and look at the full month of March 2026, what you find is a pattern that nobody in the mainstream media has bothered to stitch together. At least 6 significant fireball events over or near the United States in roughly 20 days. 6. Not a slow news week of distant fireballs. Multiple high-energy events. Multiple sonic booms. At least 2 confirmed meteorite falls. And 1 possible house strike in suburban Texas. None of them connected to any known meteor shower. All of them arriving unannounced. We are not here to tell you the sky is falling. We are not going to call this a cover-up or claim the government is hiding something in a hangar somewhere. What we are going to do is look at what the data actually shows, ask the questions that the official press releases have not answered, and explore one hypothesis that is quietly circulating among researchers, but has not made it onto your news feed yet. Because the real question is not whether these events happened. NASA confirmed them. The radar data confirmed them. The seismographs confirmed them. The question is why they are all happening now, in the same window, over the same country, with no connection to any predictable source. And Houston, it turns out, might be the most important piece of this entire puzzle. Not because of the boom, not because of the shaking, but because of what showed up on the radar afterward. That is where this story gets genuinely strange. The Houston event had all the hallmarks of what scientists call a bolide, a particularly bright and energetic fireball that typically produces an audible shockwave. But it had something else too, something that separated it from the routine category of cool space rock burns up, nobody worries. It had physical evidence, a lot of it. Here is the sequence as it unfolded. At 4:39 p.m. Central Daylight Time on March 21st, a 1-ton meteoroid became visible at approximately 49 miles altitude above the Texas Gulf Coast. That is well above where commercial aircraft fly. It was moving fast enough to cover the distance from New York to Los Angeles in about 6 minutes. By the time it reached 29 miles altitude, it fragmented, broke apart into pieces, the way a boulder might shatter when it hits pavement, except this pavement was air, and the speeds involved were so extreme that the pressure wave alone is capable of producing an explosion equivalent to a small artillery shell. The sky lit up in broad daylight. People who were outside in clear conditions, and it was a clear afternoon, no storms to confuse anyone, saw a flash intense enough to make them look up. Then came the delay. Then came the boom. That flash then boom sequence is important because it tells you something real about the physics of what happened. Sound travels roughly a mile every 5 seconds. If you are 30 miles from where a meteor breaks apart, you are going to hear that boom about 150 seconds after you see the flash. Witnesses across the Houston region reported exactly that sequence: flash, pause, then a deep concussive sound that rattled windows and, in some cases, knocked items off shelves. One woman in the Spring area, which sits in the northern suburbs, said it shook her house so hard she initially thought a transformer had exploded nearby. We will come back to what she found afterward, because that is a whole separate chapter in this story. NASA confirmed the event through their Space Alerts network with unusual speed. The confirmation included specific entry parameters: first detection at 49 miles altitude, fragmentation at 29 miles, approximate mass of 1 metric ton, velocity of approximately 35,000 miles per hour. For a space rock, 1 ton sounds small, but 1 ton of dense rock moving at Mach 45 carries kinetic energy equivalent to roughly 20 tons of TNT when it enters the atmosphere. The energy release is not just from mass, it is from velocity squared. Speed is the multiplier that turns a washing machine-sized rock into an atmospheric event felt across a 150-mile radius. Here is a detail worth dwelling on. The event happened in daylight, under clear skies, over one of the most populated regions in the southern United States. The fact that it was visible at all in those conditions means it was extremely bright, brighter than the full moon, possibly brighter than Venus at its most luminous. A nighttime event of this magnitude over a rural area would have been spectacular. A daytime event of this magnitude over a major city is a different animal entirely, because it means the energy release was intense enough to punch through ambient sunlight. That is not a small rock quietly fizzling out. That is a significant atmospheric impact. But the most important piece of the Houston story was not the flash, and it was not the boom. It was not even the eyewitness accounts, as consistent and compelling as they were. The most important detail came from an instrument that was not even designed to detect meteors. It came from something that is normally pointed at clouds, and what it found raises a question that nobody in the press conference circuit has answered yet. Doppler radar is built to track precipitation. It works by bouncing microwave signals off water droplets and ice crystals and measuring how they move. A rain shower shows up as a smear of color on the screen. A thunderstorm shows up as a rotating blob. What Doppler radar is absolutely not designed to detect is a solid object falling through the sky at high velocity. Except sometimes it does exactly that. Following the Houston event, meteorologists and citizen scientists analyzing the regional Doppler radar data noticed something that should not have been there. In the area between the Willowbrook and Northgate Crossing suburbs of northwest Houston, the radar showed a return signal consistent, not with rain, not with weather, but with a debris field of solid fragments descending through the lower atmosphere. NASA subsequently confirmed this. The agency specifically noted that fragments had been tracked by Doppler in that corridor, pointing toward a potential strewn field, which is the technical term for the elliptical zone on the ground where meteorite fragments are expected to land after a fragmentation event. Let's slow down here for a second, because the significance of this is easy to miss if you are not familiar with how rare it is. Doppler radar detecting meteorite fragments in flight is extraordinarily uncommon. It has happened with only a handful of documented falls in recorded history. The Sutter's Mill meteorite, fall in California in April 2012, is one of the most famous examples. Radar tracking of the fragments allowed scientists to recover samples within days, and those samples turned out to be among the most scientifically valuable meteorites ever collected. The Sutter's Mill fall generated enormous excitement in the planetary science community, precisely because radar-tracked recoveries give you fragments that have had the least possible time to be contaminated by Earth's environment. For radar to detect falling meteorite fragments, you need pieces that are large enough and dense enough to produce a return signal distinguishable from noise. Small porous fragments, the kind that crumble during entry, generally do not show up. What does show up are solid, dense pieces that have survived the violence of atmospheric fragmentation, decelerated to what scientists call dark flight, meaning they have dropped below the speed where ablation occurs, and are essentially falling under gravity like any other rock. The radar evidence from Houston suggests that at least some fragments made it through. Not just through the upper atmosphere where most meteors burn up, but through the entire column of air, all the way down to altitudes where radar can resolve them as distinct objects. In the location of that strewn field, directly over densely populated suburban neighborhoods. Willowbrook and Northgate Crossing are not empty fields. They are subdivisions full of houses, schools, shopping centers, and people who had no idea a debris field was potentially raining down on them from 29 miles up. You might be thinking, well, if fragments were falling, wouldn't we know? Wouldn't something have been hit? And that brings us to a woman in Spring, Texas, who walked into her living room and found a hole in her ceiling that had not been there before. The story came out within roughly 48 hours of the Houston event. A woman living in the Spring area of the northern Houston suburbs reported that she had heard the boom like everyone else, dismissed it, and then later discovered something she could not explain. There was a hole in her roof, a corresponding hole in her ceiling below it. And on the floor of her living room, near the television set, was a dark, dense, unusually heavy rock that had not been there before the boom. She contacted the fire department. The responding crew examined the object and, according to reports, described it as an unusual rock with no obvious terrestrial explanation for how it got there. The exterior of the object was reportedly dark, potentially consistent with what geologists call a fusion crust, which is the glassy, scorched outer layer that forms on a meteorite when the exterior material melts and resolidifies during atmospheric entry. The trajectory of the object through the roof and ceiling, landing several feet from the point of penetration, was consistent with an object arriving at a steep angle with significant but decelerating velocity. Exactly what you would expect from a fragment in dark flight after a fragmentation event at 29 miles altitude. Now, the critical disclaimer, and this one really matters. As of the time this script was written, no scientific institution had officially confirmed the Spring, Texas rock as a meteorite. That process takes time. A geologist needs to examine the mineralogy, the crystal structure, the ratio of iron and nickel, and ideally the isotopic composition. Plenty of rocks that people excitedly report as meteorites turn out to be what collectors call meteor wrongs, terrestrial rocks that look unfamiliar or have an unusual weight or color. Industrial slag, magnetite nodules, and iron-rich concretions get mistaken for meteorites constantly, even by people who should know better. But here is where the circumstantial case becomes genuinely compelling, even without lab confirmation. The timing lines up exactly with a confirmed atmospheric fragmentation event. The location sits directly within the radar-confirmed strewn field corridor. The physical description of the object matches the expected characteristics of a stony or stony iron meteorite. And the trajectory of the impact through the roof is consistent with a high-angle descent rather than a horizontal throw or a vertical fall from a low height. Any one of those factors alone would be interesting. All four together, occurring simultaneously, in the same location, on the same afternoon, that is not easy to wave away. If confirmed, this would be only the second house strike by a meteorite in a 13-day window globally. 8 days earlier, a meteorite had struck a house in Germany. House strikes are extraordinarily rare under any circumstances, perhaps a handful per decade worldwide, given that most of Earth's surface is ocean, forest, or open land. 2 in 13 days on different continents would be a genuinely anomalous cluster by any statistical measure. And it did not start with Houston. It started 4 days earlier, over a lake in Ohio, with an explosion that most people never heard about. An explosion that, as it turned out, was just the opening act. March 17th started as an ordinary Monday morning in northern Ohio. People were commuting. Schools were opening. The kind of Tuesday that disappears from memory the moment it ends. Then, at 8:57 a.m., a 7-ton asteroid traveling at approximately 45,000 miles per hour entered the atmosphere over Lake Erie and began to disintegrate above the farmland south of Cleveland. The energy release has been estimated at between 250 and 370 tons of TNT equivalent. That is an enormous number. For context, the conventional munitions carried by a B-52 bomber on a full payload run total somewhere around 30 tons. The Ohio bolide released roughly 10 times that energy, silently, above the clouds, before anyone had any idea it was there. The shockwave reached the ground across multiple states. Ohio, Pennsylvania, Michigan, and Indiana all recorded reports of shaking structures, rattling windows, and inexplicable booming sounds that prompted emergency calls to police and fire departments, who had no answer for what had happened. Seismic sensors registered the event. GOES-19, one of the National Oceanic and Atmospheric Administration's geostationary weather satellites, captured the optical flash. Here is the detail that planetary defense researchers find most sobering. The fragments hit the ground. This was not an event where the object fully vaporized in the upper atmosphere. Confirmed meteorite fragments were recovered from the area around Valley City, Ohio. That means a 7-ton rock, traveling at 45,000 miles per hour, not only survived entry, but delivered solid material to the surface, in daylight, over a populated state, with zero advance notice. The reason for the zero advance notice is not negligence. It is physics. Objects smaller than about 30 to 50 meters across are effectively invisible to our current survey systems until they get very close, and even then, only if they are approaching from a direction other than roughly the same direction as the Sun. The Ohio asteroid came in on what is called a sunward approach, meaning it arrived from the general direction of the Sun relative to Earth, putting it in the optical blind spot that has existed in planetary defense for decades. Ground-based telescopes cannot stare at the Sun. Space-based assets that could theoretically fill this gap exist in concept, but not yet in sufficient operational capacity. The Ohio rock arrived from exactly the direction we cannot see, at a size below the threshold most survey programs prioritize, and it hit us before a single alert could be generated. And the uncomfortable truth is this: the Houston event, 4 days later, showed the exact same failure mode. Different direction, different size, same result. No warning, no detection, just an impact, and then confirmation after the fact. If this were a one-off, you could call it bad luck and move on. But when you pull back and look at the full timeline of what happened in the weeks surrounding these two events, bad luck starts to feel like an insufficient explanation. Because Ohio and Houston were not alone, not even close. Pull up any Fireball reporting database and filter for the month of March 2026, and what you find is a timeline that does not look like a normal month. It looks like something changed. The clustering started showing up in mid-February, with earlier reports near the Ohio corridor, though nothing as energetic as what was coming. Then March arrived, and the pace picked up. Around March 2nd, a significant fireball event was reported over Louisiana. The following day, March 3rd, the Pacific Northwest experienced a sonic boom event, consistent with a bolide entering the atmosphere. Not just a faint flash at the edge of camera frames, but a pressure wave, audible across a wide geographic area. On March 8th, Europe registered its own event. A meteorite fall in Germany that, as mentioned earlier, sent at least one fragment through a residential roof. By March 11th, the American Meteor Society had logged over 113 separate witness reports for a single fireball event. March 20th brought a major event over the South Pacific, and then March 21st delivered Houston. That is at least 6 high-energy events across 3 weeks, distributed across multiple continents, producing physical evidence on the ground, fragments, sonic booms, radar returns, structure damage, at a rate that is far above the statistical baseline for any comparable 20-day window in recent memory. Under normal circumstances, the global rate of meteorite-producing falls, meaning falls that put actual rock on the ground, runs at roughly 5 to 10 confirmed events per year. In March 2026, that rate was being approached or exceeded in a single month. Now, you might be thinking, surely this has been reported. Surely somebody has put these events on a timeline and asked an official what is going on. And the answer is, not really. Each event was covered individually, as a local curiosity. Boom over Ohio. Interesting. Here is NASA's statement. Boom over Houston? Wow. Did you feel that? What nobody in the mainstream press did was step back and ask why 6 of these things happened in the same 20-day window, across the same patch of the solar system, with no connection to any established astronomical source. That is the question that makes scientists uncomfortable. Not because they are hiding something, but because they do not have a clean answer. And here is why the absence of an answer matters. None of these events can be explained by the most obvious explanation for clustered meteor activity, which is a meteor shower. Not even close. Meteor showers are predictable. They happen every year on roughly the same dates because Earth passes through the same debris trails left behind by comets. The Perseids peak every August. The Leonids peak every November. The Geminids light up mid-December. Every major shower has a radiant, a specific point in the sky from which all the meteors appear to originate, because all the particles are traveling along parallel paths relative to Earth. If you trace the streaks backward, They all converge on the same spot. That convergence is what defines a shower. It is a signature. It is identifiable. The March 2026 events do not have a radiant. The Ohio bolide came in on a sunward approach from one direction. The Houston meteor came in from a different trajectory entirely. The Pacific Northwest event came from yet another direction. The German fall had its own geometry. When researchers mapped the entry vectors, they did not converge on a point. They scattered. They pointed in different directions, like events arriving independently, rather than as members of a coherent debris stream. That is the first reason this is not a meteor shower. The second reason is that there is no major active shower in this time window associated with this region of the sky. There is a minor shower called the Gamma Normids that peaks in early March, but it is a weak shower primarily observable from the southern hemisphere, with typical rates of only a few meteors per hour at peak, and the energies involved in the March 2026 events are orders of magnitude beyond anything associated with Gamma Normid activity. So the shower explanation does not hold. What we appear to be looking at is an elevated rate of what astronomers call sporadic meteoroids, random objects that have no association with any known cometary debris trail. Sporadics are always present. On any given clear night, you can see a few if you look long enough. They come from all directions because they represent the general background population of small rocks on independent orbits that happen to intersect Earth's path. Normally, they arrive at a relatively steady background rate. Occasionally, Earth passes through a slightly denser region of interplanetary space, and the rate ticks up. But here is the problem with applying that explanation here. The clustering in March 2026 is so pronounced, so geographically concentrated, and so energetically significant that the "we just hit a dense patch" explanation starts to look inadequate. And if it is not a shower, and if it is not a dense patch, then what is it? That question leads to a statistical problem that nobody is comfortable discussing out loud. Let's talk numbers, because this is where the strangeness becomes hardest to dismiss. Under normal background conditions, the global rate of confirmed meteorite falls, meaning events where physical material reaches the ground and is documented, is approximately 5 to 10 per year. That works out to roughly 1 every 5 to 7 weeks, on average, distributed randomly across the planet. For 2 confirmed falls to occur within 4 days of each other over the same country would already be unusual. For that to happen while a third probable fall is occurring in suburban Houston, while a fourth hit a house in Germany 2 weeks earlier, while sonic boom events are being reported across multiple continents in the same month, the probability of that being random coincidence starts to compress towards something genuinely small. Here's the counterargument, and it is an honest one. We live in an era of unprecedented documentation. Every person carries a camera in their pocket. Doorbell cameras, dash cams, and security systems record continuously. Social media propagates unusual events at the speed of light. It is absolutely true that many events which would have gone unrecorded in 1986 are now captured, shared, and reported in 2026. So some of what looks like an increase in fireball activity might actually be an increase in fireball awareness. More cameras means more footage. More footage means more reports. More reports can look like more events, even if the underlying rate has not changed. That argument is valid for raw eyewitness reports. It falls apart when you apply it to physical evidence. Cameras do not create meteorites. Dashcams do not generate seismic readings. Social media does not produce Doppler radar returns. The Ohio fall produced confirmed fragments on the ground, verified by geologists. The Houston event produced a Doppler-confirmed debris field. The German event produced a confirmed house strike. These are not reports. These are physical artifacts. The physical evidence rate for March 2026 is elevated above the statistical norm in a way that cannot be explained by better cameras or more eyewitnesses. Something produced more material. And that raises the uncomfortable question of whether the source of that material is something we have already identified or something we are only beginning to understand. The official explanation is straightforward and reassuring, but it has a crack in it, a small one, and cracks have a way of widening when you push on them. The standard scientific position on elevated fireball activity is grounded in well-established orbital mechanics, and it is worth taking seriously before we go anywhere else. The solar system is not empty. Between Mars and Jupiter sits the asteroid belt, a region containing millions of objects ranging from dust grains to bodies hundreds of kilometers across. These objects are not static. Over millions and billions of years, gravitational interactions with Jupiter, Mars, and the other planets gradually shift their orbits. Some of those shifted orbits become Earth-crossing paths. The objects that follow those paths are called near-Earth objects, and there are hundreds of thousands of them, most too small to be tracked. When Earth passes near a denser node in that population, a region where orbits happen to cluster due to resonance effects with Jupiter, the number of inbound objects ticks up. According to NASA and the broader planetary science community, the most probable explanation for the March 2026 cluster is exactly this mechanism. A temporary increase in Earth's passage through a region of slightly elevated near-Earth object density, sourced from the asteroid belt, explained entirely by long-term orbital drift and gravitational mechanics. No new physics required, no exotic sources invoked, just the predictable consequence of living inside a solar system that still contains a lot of small rocks moving on complex paths. This explanation has the enormous advantage of being consistent with everything we already know about how the solar system works, and it requires no new assumptions. In science, the explanation that requires the fewest new assumptions is generally the one you start with. But here is where a small, persistent problem shows up. This mechanism operates on timescales of thousands to millions of years. It does not generally produce a localized spike in high-energy events over a 20-day window in a specific geographic region. The asteroid belt's contributions to Earth's impact rate should be relatively smooth on human timescales, not clustered into bursts. So when scientists say probably asteroid belt debris in elevated orbital density, what they cannot easily explain is why that density spike appears to be concentrated in early March 2026 rather than distributed evenly across the preceding and following months. The explanation accounts for the source. It does not fully account for the timing, and the timing is precisely what needs explaining. Before we get to the hypothesis that nobody in the mainstream is talking about, we need to genuinely grapple with the strongest counterargument, because if we dismiss it too quickly, we are just telling you what you want to hear. The reporting bias argument goes like this. Human attention is contagious. When one fireball makes the news, millions of people suddenly start looking up, checking apps, and filing reports for things they would have ignored the week before. After the Ohio event on March 17th, fireball reporting across the United States spiked, simply because people became aware that this kind of thing happens, and that their observations were valuable. The Houston event 4 days later caught far more witnesses, partly because millions of people in the region were already primed to look up and notice. This is a real phenomenon. Scientists who study fireball reports call it the Ohio effect informally, the way a high-profile event temporarily inflates the number of subsequent reports by raising public awareness. The American Meteor Society regularly issues reminders after major events that an apparent increase in reports does not necessarily mean an increase in actual events. More people looking means more things get noticed. The sky did not suddenly get busier. Our collective attention did. This explanation handles the soft evidence well. It accounts for the spike in eyewitness reports. It explains why social media seems to be flooded with fireball videos in the days after a major event. It is entirely reasonable and scientifically defensible, and you should hold it in your mind as a genuine possibility throughout everything that follows. The problem is that it cannot account for the hard evidence. You can amplify attention. You cannot amplify energy. The Ohio bolide released the equivalent of 300 tons of TNT, and that number comes from satellite optical data and seismic readings, instruments that do not get influenced by whether people are talking about fireballs on social media. The Houston event's Doppler radar signature does not care whether 1 million people were primed to report unusual sights after Ohio. Radar detects mass. It detected mass. The recovered fragments from Ohio do not become more real because more people were paying attention. They were recovered. They exist. The physical evidence rate in March 2026 is elevated, and no amount of increased public awareness created the physical evidence, which means something else did. And that something else might be connected to a visitor that arrived in our solar system several months ago, one that almost nobody outside of astronomical circles noticed. In October 2025, astronomers detected an object moving through our solar system on a trajectory that could not be explained by any solar origin. Its speed and path were inconsistent with an object bound gravitationally to the Sun. The designator assigned to it was 3I Atlas, and it became only the third confirmed interstellar object ever detected passing through our solar system, following the famous Oumuamua in 2017 and Borisov in 2019. 3I Atlas was traveling faster than solar escape velocity, meaning it was not visiting, it was passing through, and it brought whatever it carried with it. Here is the hypothesis, and to be absolutely clear, this is speculative. It has not been confirmed. It has not been published as a peer-reviewed conclusion, and the researchers who discuss it do so carefully and tentatively. The idea is this: interstellar objects do not travel alone. Just as comets in our own solar system are embedded in broader clouds of smaller debris, an interstellar visitor could theoretically be accompanied by, or could have scattered ahead of it, a cloud of associated smaller material, fragments, grains, pebbles, and meter-scale rocks that share its general trajectory. As Earth moved through a region of space that this debris might occupy, the interaction rate with that material would temporarily increase. The timing is suggestive in a way that is hard to ignore. 3I Atlas was detected in October 2025. Earth's orbital path would bring it into closest alignment with the general trajectory of interstellar debris associated with that object somewhere in the window from late 2025 through mid-2026. March 2026 sits squarely in that window. The lack of a common radiant among the March events, the fact that the Ohio and Houston and Pacific Northwest events came from different directions, could be consistent with a dispersed debris cloud rather than a coherent stream, since material scattered by gravitational interactions with Jupiter or Saturn during the approach would be spread across a range of trajectories by the time it reached Earth's orbit. Jupiter's role in this potential scenario deserves a mention. The largest planet in the solar system acts as both a shield and a scattering mechanism. When interstellar debris enters the inner solar system, Jupiter's gravity can deflect some of it away from Earth and scatter some of it toward Earth, depending on the geometry of the approach. A scattering event caused by Jupiter could explain both the multi-directional arrival angles and the apparent concentration in a narrow time window. This is not wild speculation. It is the same mechanism that explains how cometary debris gets redirected into Earth-crossing orbits in the first place. The mechanism is known. Only the source material is new. But here is the thing about a hypothesis. It lives or dies on evidence. And there is one type of evidence that would settle this question definitively. One piece of data that could tell us whether the March 2026 events were business as usual, or something genuinely unprecedented in recorded history. That evidence may already exist. The question is whether anyone has analyzed it yet. If you want to know where a rock came from, really know, not just guess, you look at its chemistry. Specifically, you look at its isotopic composition. Isotopes are variants of the same element with different numbers of neutrons in their nuclei, and different regions of the universe produce different ratios of isotopes depending on the nuclear processes that forged them. Rocks formed in our solar system carry a characteristic isotopic signature, a chemical fingerprint shaped by the conditions around our particular star 4.5 billion years ago. Rocks from outside our solar system, forged in a different stellar environment, would carry a different signature. Not radically different in most cases, but measurably different if you have sensitive enough instruments and samples that have not been contaminated by Earth's environment. This is why the fragments recovered from the Ohio fall matter enormously, and why the potential Texas fragment matters even more if it is confirmed. The Ohio meteorites have been in the hands of researchers for days. Whether those researchers have prioritized isotopic analysis, which is a more time-consuming and resource-intensive process than standard mineralogical classification, is not publicly known. If the Ohio fragments carry an isotopic signature consistent with solar system formation, that would be a significant piece of evidence against the interstellar hypothesis for at least that event. If the signature is anomalous, even slightly outside the range of known solar system materials, the implications would be almost impossible to overstate. The German Haus Strike meteorite from earlier in March is presumably also under study, with European researchers likely working through the standard classification process. The Texas fragment, if confirmed as a meteorite, would represent a third potential data point from roughly the same time window, potentially recovered with minimal ground contamination, given how quickly it was identified. 3 contemporaneous samples from a potential debris cluster would be an extraordinary data set for any lab that gets access to them. The frustrating reality is that isotopic analysis takes weeks to months. Lab time is competitive. Results are published on academic timelines, not news cycle timelines. So the answer to whether March 2026 represents a normal fluctuation or something genuinely new may already be crystallizing inside a mass spectrometer somewhere, and we just do not have the results yet. If those results come back normal, this is a fascinating but explainable chapter in Earth's impact history. If they come back anomalous, the scientific community will have a lot of very urgent conversations to have. And while those conversations take place in labs and conference rooms, a very different and very practical problem continues to exist in the world above all of our heads. Here is the fundamental truth about planetary defense in 2026. We are very good at tracking large objects. The SpaceGuard and related survey programs have cataloged the vast majority of near-Earth asteroids larger than 1 kilometer, the city killer and civilization-threatening class. We know where most of those are. We have modeled their orbits for decades into the future, and none of the known large ones are heading toward us on any short time scale. That is genuinely reassuring information and represents a real achievement by the global astronomical community. What we are not good at, what we are, to be direct about it, essentially blind to, is the size range between about 1 meter and 50 meters. Objects in that range are too small to reflect enough light to be detected by most survey telescopes until they are already very close to Earth, sometimes only hours before entry. The Ohio asteroid was 7 tons, roughly 3 to 4 meters in diameter. The Houston meteor was 1 ton, perhaps 1.5 meters. Both are well within the detection gap. Both were invisible until they hit. And both events unfolded in the same month, demonstrating that this is not a theoretical vulnerability, but an active one. The sunward blind spot compounds the problem. A significant fraction of Earth-crossing objects approach from the general direction of the Sun, simply because of the orbital geometry of the inner solar system. Ground-based observatories cannot stare at the sun, so any object on a sunward approach has a structural advantage over our detection systems that has nothing to do with its size. Several proposed space-based infrared survey missions have been designed specifically to address this blind spot by operating from a vantage point that gives them a sunward field of view. These missions exist in various stages of proposal, funding negotiation, and development. As of March 2026, none of them are operational. The gap remains open. The sobering implication of Ohio and Houston happening back-to-back is not that something changed in the sky. The implication is that nothing changed in our systems between the two events. Whatever allowed the Ohio rock to arrive unannounced on March 17th had not been fixed by March 21st. We had 4 days to absorb the first event, and then the second one happened anyway, the same way, through the same gap, with the same result. A call from NASA telling us what just happened rather than what was about to happen. And this is occurring against a backdrop of space weather conditions that, in the same week, were doing something quite unusual on their own. In the same window as the Ohio and Houston events, Earth was experiencing what meteorologists classify as a G3 geomagnetic storm, the third level on a 5-point severity scale, significant enough to affect satellite operations, GPS accuracy, and high-frequency radio communications. Solar wind pressure was running at roughly 8 times normal magnetic field intensity. Auroras were visible at latitudes far below where they are typically seen. Reports came in from states and countries that almost never experience the northern or southern lights, places where the aurora is not a normal feature of the night sky under any typical conditions. To be clear, and this genuinely matters, there is no confirmed scientific mechanism linking elevated solar wind activity to an increase in meteor or asteroid impacts. These are separate phenomena driven by separate physics. Geomagnetic storms are caused by solar activity, coronal mass ejections, and elevated solar wind, and they affect Earth's magnetic field, not the rate at which rocks arrive from interplanetary space. A G3 storm does not pull asteroids toward us or deflect them in our direction. The two categories of events are essentially unrelated in terms of direct causation. And yet, multiple significant anomalies in Earth's near-space environment were occurring simultaneously in mid to late March 2026. Elevated fireball activity, a major geomagnetic storm, unusual aurora activity. In the same days, seismographs in several regions recorded minor but notable ground motion events that caught the attention of researchers tracking correlations between space weather and seismic activity, a correlation that remains scientifically contested but has not been definitively ruled out. None of this proves a connection. Correlation is not causation, and that principle exists for good reasons. But when multiple unusual things happen at the same time, even without a known causal link, the pattern is worth noting, because sometimes patterns precede explanations. And sometimes the most interesting question is not what caused something, but what else was happening when it did. Something else was happening very close to home, in terms of cosmic distances, in the same week. Something that passed us by in the dark, close enough to matter. On the same week that Ohio shook and Houston boomed, an asteroid designated 2026 FU made a close approach to Earth at approximately 1.5 lunar distances, 1.5 times the distance between the Earth and the Moon. In astronomical terms, that is not an emergency. Objects pass at lunar distances regularly without incident, but the designation tells you something important. 2026 FU received its designation in 2026, meaning it was discovered recently. It was not a rock that had been on the catalog for decades, with a well-modeled orbit. It was a late detection, found relatively close to its closest approach, which is precisely the failure pattern that planetary defense researchers have identified as the most concerning. late detection is not the same as close detection. A rock discovered 2 weeks before its closest approach is not dangerous, simply because it was discovered late. The danger comes if the trajectory turns out to involve an impact, at which point 2 weeks is not enough time to mount any meaningful response. The 2026 FU approach was safe, but the lateness of its discovery illustrates the same principle as Ohio and Houston. We are seeing objects later, not fewer. The detection technology is improving, but not fast enough to close the gap between "we found it" and "we have time to do something about it." Several other close approach events were cataloged in the same week, a detail that received almost no attention in the mainstream press, which had already moved on from the Ohio story by the time Houston happened, and from the Houston story within 48 hours of that. The rhythm of news is event, reaction, next thing. The rhythm of planetary defense is years of preparation for a moment that might come without notice. Those two rhythms do not naturally synchronize. What March 2026 made briefly visible, before the news cycle moved on, is the size of the gap between them. And that gap is not abstract. It is the gap between a warning and a phone call explaining what just happened. Which brings us to what all of this actually means, and what, if anything, you are supposed to do with it. Let's return to the title, because it deserves an honest answer. What are they not telling you? The answer is probably not what you clicked for if you arrived expecting a cover-up. There are no suppressed files. There is no secret database of inbound objects that NASA is tracking and not disclosing. The agency published its confirmations of both Ohio and Houston quickly and transparently. The radar data was available to anyone who knew where to look. The fragment recovery from Ohio was confirmed publicly. The institutions behaved the way institutions generally behave when something falls from the sky. They measured it, confirmed it, and issued a statement. What they are not telling you, because in many cases they genuinely do not know, is why this month is running so far above normal. The three most plausible explanations, ordered from most to least conventional, are these. First, a statistical spike. Clusters happen in random distributions, and this might simply be an unusual but not impossible concentration of events that will regress to the mean in April and May. Second, a temporary increase in local debris density. Earth may be passing through a slightly denser node in the near-Earth object population for reasons that have nothing to do with anything exotic, just the normal but poorly mapped texture of interplanetary space. Third, the interstellar debris hypothesis, the passage of 3I Atlas, and the potential scattering of associated material into Earth-crossing trajectories, which would be unprecedented in recorded history and would require the kind of isotopic confirmation that is currently being processed in laboratories that have not yet published their results. The honest answer is that all three of these could be partially true simultaneously. Statistical clustering, local density variation, and an exotic source contribution could all be contributing factors to what happened in March 2026, weighted in ways that we do not yet know. The real mystery is not whether the events happened. It is why they happened now, in this window, at this rate, and the potential Texas fragment, sitting somewhere in a lab or in an evidence bag or on a researcher's desk, may be carrying the answer in its chemistry, in the ratio of isotopes baked into it during the stellar processes that forged it, possibly in a solar system other than our own. Houston may not be the end of this story. If the interstellar debris hypothesis has any truth to it, or if the local density spike has not yet peaked, or if the statistical cluster has more events yet to discharge, there is no particular reason to think March 21st was the last one. The detection systems that failed to see Ohio coming did not improve before Houston arrived. They have not materially improved since. The next event, wherever and whenever it comes, will almost certainly follow the same sequence. entry, explosion, confirmation, statement. The only thing that changes is which city is underneath it. The next one will not be detected either. The only question is when. And whether, by the time it comes, anyone will have finally decided that the gap between watching the sky and actually seeing it is worth closing, before the sky decides to make the point for us, one shockwave at a time.